Previously, we examined the parent function of y equals x squared, our quadratic function. What we're going to do now is look at some other quadratic functions, this time in factored form versus standard form, and examine a couple of key features, in particular the x-intercepts and y-intercepts, and complete some sketches for the graphs and notice any patterns that exist. So at this point, you should have already looked at sketching the graphs in part 1, and we're just going to recap and make sure everything is on target and look at any patterns that maybe you've come across. So the first equation we were looking at was y equals x minus 4 times x plus 2. Again, this is in factored form. So what do we see in this graph? Well, in this graph, we notice that the x-intercepts were at negative 2, 0, and 4, 0. The y-intercept happened to be at 0, negative 8. We could also say that this quadratic function is concave up. We can see the vertex is at 1, negative 9. The axis of symmetry would be at x equals 1. Notice how the domain is unchanged from the parent function. That's still from negative infinity to positive infinity within your parentheses. So it's saying all real numbers for the inputs. Our domain did change because it looked to get shifted down. I'm sorry, range change, it got shifted down. So we would say our range would be a bracket, negative 9, comma, positive infinity parentheses. And we have our accurate sketch. We've got some good data points plotted. And so this is what we were looking for when we were graphing these functions. Now our next equation was y equals x minus 3 times x minus 3. What happened to your graph? Well, if you notice, our x-intercepts are at 3, 0, 3, 0. Again, remember, it's touching the x-axis and it's being used on the negative, the decreasing interval, and your increasing interval. That's why we're listing it twice. We can see our y-intercept is at 0, 9. Then we looked at the equation y equals x times x plus 5. Or perhaps you wrote this as parentheses x plus 0 times x plus 5, and what resulted in your graph? Well, here in our graph, we can see we've got x-intercepts at negative 5, 0, and 0, 0. We also have our y-intercept at 0, 0, and this function is still concave up. We have one more function for this part. Y equals our quantity 2x plus 1 times our quantity x minus 4. That graph had x-intercepts at negative 1/2, 0, and 4, 0. The y-intercept was at 0, negative 4. And again, this parabola still is concave up. So thinking about the parent function and these new 4 functions, what's the connection between the factors in the equation and the x-intercepts you see on the graph? How can you use this to predict where the graph would cross the x-axis? So again, with our parent function, y equals x squared, we saw that we had the 2 x-intercepts at 0, 0. Then with these 4 functions, hopefully you noticed how the graph was changing in terms of the x-intercepts, and you saw some patterns between the x-intercepts and the equations. Hopefully you saw that if you set each factor equal to 0 and solve for x, you would then have the x value for the coordinate of the x-intercepts. For example, the last equation we're looking at, y equals our quantity 2x plus 1 and our quantity x minus 4, we can clearly see the 2 factors being used, 2x plus 1 and x minus 4. If we take each factor and set it equal to 0, again, 0 because the x-intercepts have an output of 0, and undo them to solve for x. If it was 2x plus 1, you would have to subtract 1 from each side and divide by 2. That's how we got the negative 1/2. And if it was x minus 4, you add 4 to each side. That's how we got the 4. Notice those are the x values for the coordinates of your x-intercepts. So again, we should be able to look at an equation in factored form. So with this pattern in mind, we now could predict the locations of where our functions that are quadratic cross the x-axis, which are your x-intercepts, without having to do the graphing feature. So in this portion for step 6, here we have 3 quadratic functions in factored form. Could you predict where they would cross the x-axis? So in other words, can you tell me the locations of the x-intercepts without looking at their graphs? Well, if we use the same technique that we talked about before, taking each factor of the functions and setting them equal to 0, we should be able to find the x value for the coordinates for each x-intercept. And we can see that the quadratics have 2 factors. Our first function here, you can see a factor of x plus 14 and x minus 16. The second one is a factor of x minus 1 and x plus 2. And our third one has a factor of x, or think of it as x plus 0, times x minus 15. If you take each factor and set them equal to 0, because x-intercepts have an output of 0, we should be able to find the values of our x-intercepts, the inputs. So again, that's what we did here. I just took each factor and set them equal to 0 so I can solve. And if you notice, this factor here of x, we set equal to 0, we already have the input value solved for. So that's nice when that happens. So again, if we did the solving, we now have the x values of the x-intercepts for our functions, and then we can write our coordinates. So for example, we had the equation y equals our quantity x plus 14 times x minus 16. That's going to have x-intercepts at negative 14, 0, and 6, 0. Our second function of y equals our quantity x minus 1 times our quantity x plus 2 has x-intercepts at 1, 0, and negative 2, 0. Then our third function, y equals x times x minus 15, has x-intercepts at 0, 0, and 15, 0.